Okay, welcome everyone. So today's speaker in the algebra seminar is Nguyen from the University of Akron, and he's going to speak about group characters and their fields of values.
Thank you. Thank you all very much for having me. I also would like to thank Eric and Professor Nakano for setting up my talk. So my talk is in the areas of representation theory and character theory of finite groups. In particular, I will discuss about some results on the connection between structure of finite groups and the values of their characters. So let me start by reminding you what is a representation and what is a character of a group. So the representations in this talk will be complex representations only. So let's G be a finite group. A representation of G is a group homomorphism that I denote by tau from G to the general linear group of a vector space that I denote by capital V. Now, if the dimension of V is D, then this group is exactly the group of invertible D by D matrices over the complex numbers. Okay. So the idea of representation theory is to represent group elements by linear transformations or matrices, and then use linear algebra to study groups. Now the character afforded by that representation tau is simply a function or a mapping denoted by chi sub tau from the group G to the complex numbers, defined by the value of chi at a group element little g to be the trace of the matrix representing that group element G. So when we go from a representation to a character, we may think that we lose quite a lot of information because we go from an entire matrix to just the trace of the matrix. But not really. We don't lose much information actually. It turns out that if two representations have the same character, then the two representations are conjugate in the sense that the two matrices representing the same group element are conjugate by a fixed invertible matrix. And in that case, we say that the two representations are equivalent. So they are basically the same. And so we have a one-to-one correspondence between the characters and the equivalence classes of representations. But that only happens when the representing field has a characteristic 0. When the characteristic is positive, then we don't have a one-to-one correspondence anymore, and the situation is a little bit more complicated. Now there are two notions associated to a character that I want to introduce because I'm gonna talk about them quite a lot throughout this talk. The first one is the degree of a representation tau, or the degree of a character chi sub tau is that number D, the dimension of the vector space. And it's easy to see that that is also the value of the character chi at the identity element of the group, right? Because under this homomorphism, the identity element of the group is mapped to the identity matrix. And the trace of the identity matrix is nothing more than the dimension of the matrix, the size of the matrix. Another notion is the field of values of a character. It is the smallest field containing all the values of that character. So obviously, the field of values of chi here will be a subfield of C. And it is not a difficult exercise to show that the field of values of any character chi here of a group G is always a subfield of a cyclotomic field, extending the rational numbers by a primitive n root of unity, say e to the 2 pi I over n, when n is the order of the group G. Well, actually, you can take n to be the exponent of the group G if you want to make it smaller, but it's not that important. Okay. So a quick example, let me show you the character table of the alternating group of degree 5, denoted by A5. So it has 5 conjugacy classes. And here I put some representatives of those classes on the first line of the table here. And therefore, it has exactly 5 irreducible characters. And all the values of them are in this table. Now, looking at the table, you see that the field of values of chi1, chi2, and chi3 are rational numbers, right? Because all the values are rational. But the values of chi4 and chi5 are not rational anymore, slightly bigger than rational. It's the smallest field containing radical of 5. But it is still a real value character. So it turns out that all the characters of this group are real value, but only 3 of them are rational value. Okay, so the first result I would like to present is a very classical one of Burnside, saying that a finite group G has an even order if and only if the group has some non-trivial irreducible character that is a real value. Okay. So this is a very nice and clean statement. It connects the parity of the order of the group with the existence of a non-trivial real value irreducible character of the group. It's very nice. The proof of this one is actually quite simple, at least for one direction, and that is the only if direction. And I would like to take the chance here to prove it, because perhaps this is the only proof I could do in details in this talk. So so the if direction is a little bit more advanced, and we have to use the so-called orthogonality relation of characters. But for the only if direction, so let me assume that the group G has an even order. A basic formula in character theory is that the order of the group is always equal to the sum of the square of the degrees of irreducible characters of the group. Okay? And I'm going to take the trivial character outside the sum. And trivial character has a degree 1, so that's why I put 1 here. And in the sum, I'm gonna get rid of the trivial character, which is denoted by 1 sub G here. Now, if the order of G is even, then that sum is an odd number. Okay, and then I look at the action of complex conjugation. complex conjugation on the characters in the sum here. Now think about it. If a character is not real value, and then you look at the complex conjugation on that character, you're gonna have another character of the same degree, right? So let's assume that none of the characters in the sum here are real value. Then the characters here are partitioned into the pairs of two characters of the same degrees. And so when you take the sum of the squares here, it will be an even number, cannot be odd, right? And therefore, there must be at least one character, non-trivial character, that is fixed under complex conjugation. And therefore, that character is a real value, and we are done. That's what we need. So one direction is easy, but like I said, the other one, the other direction is slightly more complicated. Anyway, so it turns out that if you replace the word real here by rational, then the statement is still true. It turns out that a finite group G has an even order if and only if the group has a rational value, irreducible character. But the proof is totally different. So on another level, the only known proof that people know nowadays of that relies on the classification of finite simple groups. So it is highly non-trivial. Something stronger is even true, and that was conjectured by Richard Gao many years ago, saying that every finite group of even order has a non-trivial irreducible character with a rational value, but not only that, but it also has an odd degree. So we can put one more condition into that character. The character has an odd degree and rational value. This one was approved by Navarro and Tiep more than 10 years ago. And
it's
of course,
4:15.
It also requires the classification, because the weaker one already requires the classification. Well, Navarro and Tiep prove something stronger. They show that if a finite group has an order divisible by a prime P, then the group has a non-trivial irreducible character with a degree co-prime to P. And the values in the cyclotomic field, extending the rational number by a primitive P root of unity. And for the rest of this talk, I am going to denote that by Q sub P for convenience. You may confuse it with periodic fields, but I'm not going to use periodic fields at all in this talk. So we should be fine. Now, if P is equal to 2, then that is exactly, I mean, the theorem here is exactly Gauss' conjecture, right? Because Q sub 2 is exactly the rational numbers. So recently, we are able to extend the results here a little bit further. Instead of considering a single prime, we consider a set of two primes. And here is a result. This is joint work with Giannelli, Schaefer, Fry, and Vallejo. So we assume that pi is a set of two primes, and two primes could be the same, no problem. Then we kind of classify all the groups that have a non-trivial irreducible character of degree co-prime to pi, such that the values of that character belong to Q sub P or belong to Q sub Q. And we show that so that happens if and only if the order of the group is divisible by 2 or divisible by P or divisible by Q. Now the degree here is coprime to pi if it is coprime to P and coprime to Q. That's, I think usual notation. Now, if you take P to be equal to Q, then we go back to the theorem of Navarro-Tiep. So that's why I said that this one is an extension of the earlier results. Now, the theorem would be nice if it stops right here. However, there are a couple of exceptions. When the group has a composition factor isomorphic to a certain sporadic simple groups, like the Tisser group or the Janko group, with a particular set of primes. For example, like when the group G has a composition factor isomorphic to the Tisser group, then we need to eliminate the case when the 2 primes are 3 and 5. And also when the group has a composition factor isomorphic to J4, then we need to eliminate a couple of pairs of primes here. Now we reduce the statement here to the same statement on finite simple groups without a lot of trouble. And then we check that for some smaller sporadic simple groups by hands, because that is not too difficult. And then we go forward for the alternating groups and simple groups of Lie type. Simple groups of Lie type is slightly more difficult, but we got it. And after that, we go back to sporadic simple groups to check for the bigger groups. And for bigger groups, we have to use, computers to do it. And out of nowhere, we found a couple of exceptions. So that was a little bit disappointed. Anyway, let me mention a couple of consequences of that theorem that look cleaner and nicer. The first one is straightforward of the theorem here. If I let one of the 2 primes to be equal to 2, then we have no exceptions, right? So we can classify exactly when the group has a non-trivial irreducible character of degree odd and coprime to Q, and the values are contained in Q sub Q. And we show that that happens if and only if the order of G is odd and not divisible by Q. So this one is an extension of Gauss conjecture that I mentioned earlier. The other consequence here is not that straightforward, and it is related to a new concept, namely the p-rationality of characters. So the idea is we realize the condition on the values here by expanding the fields Q sub P and Q sub Q here. We have a nicer statement. But in order to explain this one, I need to remind you what is p-rationality and almost p-rationality. It turns out that the theorem here is also connected to a couple of the so-called global local conjectures in representation theory of finite groups that have been quite active recently. And For the next part of the talk, I'm going to explain that. So first, let me recall that a character is p-rational if its values belong to Q sub n for some natural number n co-prime to p. So basically, a character here is a p-rational if it is rational at the prime p. But it could be not rational, at other primes. That's what it is. And it is called almost p-rational if the values belong to Q sub n for some integer n not divisible by p squared. So it could be easy. So basically, the number n here is not divisible by p, or it is divisible by p but not divisible by p squared. Now, p-rational characters occur in representation theory very often. One reason is that they behave very nicely regarding the character extensions. So you have a p-rational character of a normal subgroup. In a certain nice situation, you can extend that character to the big group. So that's good. Another reason, which is more important, is that they are all fixed under this Galois group, the Galois group of Q sub the order of G over Q sub the P prime part of the order of G. Well, because all of the values belong to this cyclotomic field, right? So they must be fixed under this, and therefore they play an important role in many problems concerning the Galois accents on characters and on conjugacy classes. And one of them is the so-called MCKAY-NAVARRO conjecture that I'm going to explain in a moment. But before doing that, let me recall you the MCKAY conjecture first. This is the most basic conjecture among the global local conjectures that I just mentioned. Those conjectures propose that some important information on the representation theory of a finite group G is encoded in a local subgroup of that group G. So for the MCKAY conjecture here, the information that we are interested in is the number of irreducible representations of the group that have a degree co-prime to a prime p. And the set of irreducible representations of degree co-prime to p are denoted by EO sub p prime of G. So the conjecture here proposes that number for the group G should be the same as that number for a local subgroup, namely the normalizer of a CLOP subgroup of the group G. Okay. Now, usually the normalizer here is called a p-local subgroup, and usually it is way smaller than the group G. So the right-hand side here would be easier to compute, and once we know it, then we know the left-hand side here. Now, this one is still open, but there are a couple of breakthroughs in the last few years. For example, like more than 10 years ago, Mahler, Navarro, and Isaacs reduced this conjecture to a question on finite simple groups. Another breakthrough is more recent, I think a couple of years ago, which is due to Mahler and Spaeth. They prove this for the prime p is equal to 2. That's a very nice result. One remark I want to make here is that the conjecture here has been refined in many ways. Most of those refinements propose that there should be a bisection between the two sets here that has a certain nice property. And one of them is proposed by Navarro in 2001. He predicts that there should be a bisection between the two sets that commutes with certain Galois automorphisms. In particular, there should be a bisection that commutes with all the Galois automorphisms inside a particular Galois group here. That I think I can skip the detailed definition. The reason he proposed it because he observed that there is a similarity between the values of the characters in one set and the characters in the other set. And you know that the values are connected to the Galois automorphisms here. Another way to put it is that the license.
Can I interrupt you real quick? So there's a question. Yes.
So for the MCKAY conjecture, can you just remind me, like, if you take a finite simple group, then that the statement is still open even for finite simple groups?
Okay, so for the MCKAY conjecture, if you take a finite simple group, is this still open?
I think it was done for all finite simple groups.
Okay, so it is done. So like you said that this reduces to some statement about finite simple groups, but that's not the statement of the MCKAY conjecture. It actually proves in general. I'm just trying to clarify this.
Yes. So they reduce this statement to a lot stronger statement for finite simple groups, okay. And those things are called like reductive conditions, reductive MCKAY conditions for finite simple groups, and it is a lot stronger than the original MCKAY statement here, and that is still open.
Thanks, that clarifies.
Okay, thanks. Yes.
Okay, yeah. But I would say that even though it is still open, I mean the reductive MCKAY conditions are still open. They are verified for many families of finite simple groups already. Okay, now another way to put to put out the MCKAY-Navarro conjecture here is that the action of that particular subgroup on the two sets, permutation isomorphic. In particular, if you look at any subgroup of this group, G sub P here, then the number of characters in one set that are fixed under that subgroup is the same as the number of characters in the other set that are fixed by the same group. Right? So I'm going to look at some subgroups, and those subgroups are this one. So they are Galois group of Q sub the order of G over Q sub P to the alpha times the P prime part of the order of G, where alpha is any non-negative integer. So in order to write out and talk about the number of fixed characters under this subgroup, let me define another notion here. And I believe that this is the last one, I promise. So I want to define the so-called P-rational level of a character. It is the smallest non-negative integer alpha, so that the values of chi belong to Q sub n for some n divisible by P to the alpha. Okay. So the P-rational characters that I defined earlier are exactly those characters of level 0, to put it simply. And the almost P-rational characters that I defined earlier are exactly the characters of level 0 or 1. Okay. Now as a consequence of the MCKAY-NAVARRO conjecture, like I just explained, we're gonna see that the number of characters of level alpha in one set should be the same as the number of characters of the same level in the other set for the normalizer. And now I just focus on the case where alpha is equal to 0 and 1 only. So if alpha is equal to 0 and 1, then we have like almost p-rational characters of the group G on the left-hand side here, and the almost p-rational characters of the normalizer P on the right-hand side here. And that is the equality that I put out here. Now the next few lines are a little bit technical, so I guess I'm gonna skip them, but I just want to say that if you model the normalizer here by the so-called Fratini subgroup of P, which is the intersection of all the maximal subgroups of P, then the characters of this quotient automatically have a P prime degree and automatically almost a P rational. And that's why I didn't put the sub-index here, because all the characters are P prime degree and almost P rational. Now I assume that the order of the group is divisible by P. Let me mention that all of these are still open. I mean the first equality here. I'm just saying that it is a consequence of the Navarro conjecture. I mean MCKAY-NAVARRO conjecture. Okay, it's still open. So now I just look at a further consequence of it. I assume that the order of the group G is divisible by P. It is known for a long time that the number of irreducible characters, which is equal to the number of conjugacy classes of the group, is large compared to P. And actually, a few years ago, Navarro-Tiep proved that the number of irreducible characters of the group G should be at least 2 times the radical of P minus 1. Okay, so now you go back to the inequality here. Now, if P divides the order of the group G, then P also divides the order of this quotient. So the cardinality of the set right here is at least 2 times the radical of P minus 1. And therefore, the cardinality of this one is also at least 2 times radical of P minus 1. So the bound here is a consequence of the MCKAY-NAVARRO conjecture. Now, right after the proof of Navarro-Tiep, Mahler and Navarro-Tiep also proved the same bound for a smaller set, which is only the set of irreducible characters of P prime degree. Now, the bound that we are looking at here is even stronger because we put like the condition not only on the degree, but also on the values of the characters. I would say that we are quite close to the proof of this bound right here, but to be safe, it is still open. There are still a couple of cases for finite simple groups that Mahler and Navarro-Tiep and myself are working on. However, if we forget about the condition on the degree, but only focus on the values, so we only look at the set of almost p-rational irreducible characters, then we are able to show that the same bound holds. And we also, classify the groups when the equality occurs. Okay, yeah. So now earlier I mentioned that one of the consequences of the first theorem that I presented to you is connected to the MCKAY-NAVARRO conjecture here, and let me explain that a little bit. Let me recall that the theorem earlier is that if a finite group G has an order divisible by either P or Q, where P and Q are primes, then the group G has a non-trivial irreducible character of degree co-prime to both P and Q. And that character is almost P rational and almost Q rational at the same time. So, so this one is kind of connected to the bounds that we are trying to prove here. Now let us assume that the order of the group is divisible by P, right? So we fix a prime P and we let Q to be any other prime. Then the order of the group is divisible by P, yes. So we always, I mean, the group always has an irreducible character of degree co-prime to P here, and almost P rational, which is a character belonging to the set here. Okay, so the theorem here is an indication that, you know, there are many characters of the group G that are P prime degree and almost P rational. Of course, I'm not claiming that for different prime Qs, the characters produced by this theorem are different. That should not be the case. Sometimes they are different, but not all the time. Well, if they are different, then I guess we would be done with the bound here, I think. But that is not the case. Okay, yeah. So to finish, I just want to mention a couple of quick results on rational characters. So far, I only talk about, you know, the characters with values in a cyclotomic field. And these cyclotomic fields are extension of rational numbers by, you know, a small, I mean, they are small extension of rational numbers because P and Q are primes. So a natural question is, can we classify, you know, finite groups having a non-trivial rational character, irreducible character of degree co-prime to pi, where pi is a set of two primes? That turns out to be not an easy problem. However, in the same paper, we are able to answer it for the case when the group is solvable and the set of primes contains the prime 2. Another case we are able to show is for the alternating groups. Well, actually, for alternating groups, we are able to classify completely when the group possess you know, a rational irreducible characters of degree co-prime to pi, to both P and Q. Okay, I think that's all I have for today. Thank you very much.
Okay, thank you very much. Let's thank Hang for his talk.
Thank you.
Okay, questions?
I have one.
Okay, so
Very naive question.
yeah, Dan has a question. So I know, yeah, go ahead.
So, you know, when you take like symmetric groups, I believe the characters are all.
Yeah, so if you take the, did you hear that?
Not really.
So if you take the symmetric group, the characters are all integral?
Yes, that's right. Yeah.
So is it known like which groups have like maybe money which have, you know, which families or groups have like integral characters?
Okay, which groups have integral character tables?
Say it again, Eric.
So which groups, so do you know which groups have finite character tables? Integral character tables.
Oh, I think that is still an open problem. I believe, yeah.
So it's not hard, still, you would think maybe someone.
Okay, yes. So
The classification and everything.
yeah, even with the classification, it's still open.
Yeah, I think the complete classification is still open, but people have obtained quite a lot of results on that. I think those groups are called rational groups, if I remember correctly. And I think if a group is rational, then the order must be. I mean the prime divisors of the order of the group must be some smaller prime numbers, like 2 or 3 or 5 or 7, 11 or something like that. Yeah. So there have been quite many results on that, but the complete classification is still open.
Okay, thank you. More questions? Okay. So I don't think that's the case. So yeah, let's thank Hang again.
Thank you.
Thank you.
Thank you. So it turns out that